In this lecture, we would like to look into the relative orientation again, but this time we don't want to look into a direct solution as we have done it in the previous lecture. We want to look into a least squares approach to this computation of the relative orientation. So the goal is we want to compute the parameters of the essential matrix. That means describing 2 translation parameters and 3 rotation parameters between 2 cameras. And we want to do this with the best possible approach, which is, from the result point of view, the iterative solution in a least squares sense. And we typically build upon of the direct solution that we have computed last time. So what we typically do is we use the direct solution in order to compute an initial guess, and then take an iterative solution into account in order to get the statistically optimal result, because we can take into account the uncertainties of all the individual measurements as one of the examples of what we could not do with the 8-point algorithm, for example. So today's topic is the computation of the relative orientation using an iterative approach. Again, why was the relative orientation relevant at all? So consider you have 2 images of the same object but taken from different viewpoints, and you know a couple of corresponding points. So these are those red dots over here. So we know that this dot over here corresponds to this point over here. So this would be one corresponding pair of points. And then based on this correspondence information, we can estimate the so-called essential matrix, which encodes the rotation parameters of the camera. So how has camera 2 been rotated with respect to camera 1? And we know something about the baseline vector, so the translation. Again, as a reminder, we can only resolve this up to a scale because we can't estimate the scale of the object that we are picturing. So if we do not have any scale information, we will have this scale ambiguity. But we can compute this transformation up to the scale factor between the 2 places where the camera images have been taken. And this is something that is encoded in the essential matrix. Again, in the last lecture, we have looked into a direct method, the 8-point algorithm, in order to compute these 5 parameters. And today we want to look into a least squares approach in order to compute the parameters of the essential matrix. And this provides you with a better solution if you have, for example, uncertainty information involved and you want to take all the points into account, potential large set with different uncertainty informations, then this approach here is for you. But again, those iterative methods require an initial guess, and we use those direct methods such as the 8-point algorithm or also the 5-point algorithm in order to provide this initial guess for the iterative solution. So the direct solution still has its values. It's the standard choice. Also, if you use it together with an outlier identification technique or rejection technique such as RANSAC. But once we have done all that, we cleared our solution from outliers, then we may add a least squares approach in the end in order to get the best possible result out of that. So the topic of today is computing this iterative solution and then also discussing the quality of the results. So what about the uncertainty about those parameters? What can I say about this, at least in some special setups? Before we start, a very brief reminder about the essential matrix. So this is the matrix that we will be exploiting here in order to estimate the 5 parameters of the relative orientation for the calibrated camera. So again, the essential matrix is only there for the calibrated camera. If we have an uncalibrated camera, we would need to go for the fundamental matrix, but here we do this exercise now for the essential matrix. So the essential matrix encodes all the parameters that we can estimate from correspondences alone about the relative orientation of 2 images or the image pair, and it is in its general form written as the rotation matrix of the camera number 1, then a screw symmetric matrix encoding the baseline vector, and then the rotation matrix of my second camera. And depending on the parameterization we are now using, this can be brought into a different form. So if we use the parameterization of dependent images, then where everything is expressed, so camera 2 is expressed with respect to camera 1, then the camera 1 has the identity matrix as the rotation matrix, and then only one rotation matrix remains. But if we have another parameterization, then we come up with a different form of the essential matrix. And what is important, why is this essential matrix useful for us today? Because it encodes a so-called coplanarity constraint, which has been written down here. So if 2 points are corresponding points, so if this x prime and x double prime is an image point in image number 1 and image number 2, and we assume that those pixel locations have been generated from the same point in the environment, then this equation must be 0. So this coplanarity constraint basically allows us to check if a point pair is potentially a corresponding point. If the equation is 0, it doesn't necessarily mean that those points are corresponding points. That basically only allows us to say that they are both lying in the same apipolar plane. But if the points are corresponding, then this equation must hold. Of course, only in the noise-free case. If we have noise, it should give still values which are close to 0. And we can use this expression of the coplanarity constraint in order to estimate the essential matrix, the parameters of the essential matrix. If I know corresponding points, I can basically estimate the parameters of E, and this is what we had exercised in the direct solution, for example, using the 8-point algorithm. So how does it work? We have an n corresponding points, and then we can set up our equation for the coplanarity constraint for every single observation. This must hold for every single point pair that we are seeing. And if we use the parameterization of dependent images, then this would be our formulation, how it looks like. So the skew-symmetric matrix, which is the matrix encoding the information about the baseline vector, and the rotation matrix R, which tells us how camera 2 is rotated with respect to camera 1, assuming that camera 1, the rotation of camera 1 is the identity matrix. And we want to do this today in an iterative solution, but we don't do this for the general case because then the math can get rather complicated. We go for a slightly simplified case, namely if we are close to the stereo normal case. So the result that I'm presenting here is only the result that is valid if you start with your stereo normal case as your initial guess, assuming that your solution is not too far away from the stereo normal case. So this is, for example, the case if you have a camera installed on an airplane, you're flying the forward direction, then the individual images are roughly in the stereo normal case, depending how you set up your coordinate system, as long as you don't fly a curve, for example. Or if you have a camera installed on a car, which is looking sidewards, and you're moving in one direction, then you can also set up a coordinate system so that you're close to the stereo normal case. So we're working here for those setups. If we would go for the general solution, then the math gets more complicated and we can't see as easily the insight that we want to get from that solution today. Therefore, we are sticking here for the stereo normal case. So what I'm presenting here only holds for this stereo normal case. It's basically both cameras look into the same direction and there's only an offset in one direction, so that your apipolar lines are basically horizontal lines in an image. So every row of pixels corresponds to an apipolar line. So it's a simplified setup or simplified situation that results from the design how the cameras are actually mounted. So what we need to do for that, we need to look in the coplanarity constraint, and then the coplanarity constraint gives us with an error function, and then we can formulate it as a nonlinear least squares problem. It is nonlinear because we have our rotation parameters, for example, in there, and that means we need to iterate because we won't find the right solution with one single iteration, which would be the case if it would be linear, but we are living in a nonlinear world as so often. So we have a nonlinear error function, and again, we use the coplanarity constraint to formulate it, and we make the assumption that we are in the stereo normal case. And here, for the matter of the exercise, we are looking into the parameterization of dependent images, and we look into the classical photogrammetric parameterization. Again, here we assume that the baseline vector in the x direction is constant, so there's a constant offset in order to fix the scale ambiguity. So we're basically fixing it by setting an arbitrary value to it, by saying that bx must be a constant. As a result of this, we only have 5 degrees of freedom in our resulting relative orientation without having any constraints. So again, if you remember this classical parametrization has its disadvantages if you make movements where the movements in the x direction of the baseline vector would be 0, because this can only be compensated by setting the other values to infinity, which is something that you don't want. So, but as soon as it's, for example, the flight direction of an airplane is a local coordinate system and you're flying in the x direction, then this is not problematic. If you have completely freely moving cameras in the environment, then this may be not the right parameterization to do. For our exercise today, it is quite useful because we simply get a simple setup with 5 unknown parameters, having no additional constraints involved in there. Therefore, we are sticking here today with the classic photogrammetric parameterization. Okay, so let's get a bit more concrete. What do we want? We want to have the baseline vector and my rotation matrix as the parameters of my relative orientation for a calibrated camera. And we're assuming we are approximately in stereo normal case. That means our initial configuration is a stereo normal case, and we look into small variations from that stereo normal case. How do we obtain those parameters? We have a set of observations, and those observations correspond to pixel locations in image 1 and pixel locations in image number 2, which have been generated from the same physical point in the 3D world. So we have one object in the 3D world that generates an image or a pixel location in image number 1 and a pixel location in image number 2, and we have these correspondences. And we have n of those correspondences, assuming here have always an x and y coordinate in my image plane, and those are perfectly known. And we assume to be working in a calibrated camera. So here, those locations where I kind of leave out this index k, which stands for the camera coordinate system, that means we already have applied our calibration matrix of our camera. So we assume we have a calibrated camera in here. We also can assume that those observations here are not perfect. There is an uncertainty associated to this, and this is the uncertainty in the pixel locations. So how precisely can I actually pinpoint a point in an image that has been generated from an object? Maybe I can do this up to 1 pixel or 2 pixels or half a pixel. So this would be the uncertainty that I use to describe it here. And we typically assume that I can measure the x pixel coordinate and the y pixel coordinate in the same way, and I can measure point number 1 and point number 2, so in image number 1 and image number 2 with the same precision, so that those points typically do not vary. But in theory, we could do that. We could also say in camera image number 1, I can measure more precisely than in camera image number 2. Why could that be the case? If you, for example, have motion blur involved or other parameters which affected the image acquisition process, then in those setups, this may result in the fact that you have different uncertainties for points in different images, or every point has a different uncertainty. That's also something which can happen, because depending on the image structure, so how much gradient information typically is around the location where the key point was created, has an impact how well you can actually localize this point. So if you have strong gradients in the x and y direction, those uncertainties will be smaller. If your gradients are smaller, then the uncertainty will be larger. That's something that we have seen in terms of the point operators when we are trying to find key points which allow us to localize points very well. This was kind of a direct design decision, but the magnitude of the gradients in the image and the x and y direction tell us how precisely we can actually spot a feature location. And this can be used in those images that some points can be located better than other points, or there may be differences between 2 images. So this can be taken into account. And we assume we have an initial guess, and we assume here that this initial guess is the stereo normal case. That means we have only a shift vector, a baseline vector in the x direction, and the initial guess for the rotation of the second camera with respect to the first camera is the identity matrix, because we assume that both cameras look into the same direction, at least approximatively, and this is our starting initial configuration. So again, for the uncertainties, for now, we assume we can pinpoint all pixels in the same way, and it's basically an identity matrix multiplied with constant variance. So we have a diagonal matrix with the identical values on the main diagonal. This is a slightly simplified setup for us here, but in general, we can also take other covariance matrices into account here, and not very much will change in the solution. Okay, and again, the parameters we want to have in here is our initial parameters are the baseline vector bx is our constant, 0, 0, and the rotation matrix, the initial one, is the identity matrix. Okay, so we want to start from our initial configuration, so from this configuration down here, and then use the coplanarity constraint in order to come up with our Gauss Markov model. So how does it look like? We have our coplanarity constraint as our constraint that must hold. We have an initial guess for our parameters, and the next goal that we now have, and this will be the exercise which happens in the next maybe 10 minutes or so, is to find the equation for the Gauss Markov model. Again, this was basically that the observation plus my correction equals to some coefficient vector multiplied with the corrections in my unknown parameters. And this is then, once we have that equation, we can pull out our least squares toolbox and just follow a script and get our corrections for our parameters, for our unknowns, sorry, for unknown parameters. So how do we need to update our unknown parameters in order to come closer to our solution? And so the work that we have to put in at the user is to set up the equation for our Gauss Markov model, because once we have it from this point on time, everything follows basically up to a cookbook recipe without needing our brain to do the actual operations. Okay, so let's see how we can do this. So what we want to do is we want to look in here, in order to understand the process a bit better, into the variation of the parameters and the observations. How does it affect the function itself? So for example, if we start with our observed points, so the pixel coordinates in the first image and in the second image, then we say if we have small changes in the pixel coordinates of the point in image number 1, so it can be expressed as the coordinate that I want to have is my initial guess of the point that I have, so with what I initially started, plus a small change in this coordinate. And how does this small change look like? So we're living here in a homogeneous world. So the coordinates of the point is the x prime, y prime, and my camera constant, because I'm expressing it in the camera coordinate system. And if I change the location of a point, let's say small corrections in the image coordinates, so this will not change my camera constant, but will lead to a small update in the x and y coordinates. So with a small update in the x and y coordinate, basically I have an additive term to the x and y pixel location. So I could shift it, for example, by 1 pixel in x direction would be 1, 0, 0, the correction that I could apply. And exactly the same thing also holds for the coordinates in the second camera image, obviously. So the coordinate in the second camera images is the initial configuration that I have, plus a small update. And again, the small update is a small change in the x and y direction of that point, but not affecting the camera constant. Okay, so this was for the x prime and x double prime. Now let's look how this evolves in my unknown parameters, in my baseline vector, as well as in my rotation matrix. So let's start with the baseline vector. So our baseline vector is the initial guess of our baseline vector plus a small change in the baseline vector. So again, I have my two cameras. I have my constant offset, and so I basically have a small change in the x and that coordinate. So I could move in this direction, or I could move in this direction. These are those small corrections I can do here. Why is there a 0 here and a 0 here? That is easy. This 0 comes here from our initial guess that we said we are in a stereo normal case. And the reason why this parameter here is a 0 is a result of the classical photogrammetric parameterization of dependent images, because in this case we set the bx value to be constant in order to fix our scale parameter. That means we are not allowed to update this and change the value over here. We can only compensate this with those two values, and these are exactly the 2 degrees of freedom that I have in my baseline vector. And by having this formulation here, we don't need to add an additional constraint and add basically 3 unknown parameters. We can stick with 2 unknown parameters and no additional constraint, which makes it easier for us. And we do this because in this case, the math is easier to working with this classical photogrammetric parameterization, although this parameterization has other disadvantages as we have discussed it, especially if you have no movement in the x direction, then this leads actually to a singularity, which is something we don't want, but assuming that this is not the case, we can stick with this easier form over here. And we can also look into how does a change in the baseline vector then changes my coplanarity constraint. So the baseline vector was encoded in the screw-symmetric matrix. So the screw-symmetric matrix of my baseline vector B is my initial guess plus the small update, so these updates over here. So that means we need to compute the screw-symmetric matrix from this vector BA and the screw-symmetric matrix of this vector delta B. So, and this is the corresponding screw-symmetric matrix for this vector over here. So you can see that those 2 elements and those 2 elements are 0. And here we have the elements, the positive and negative one of the first element over here. And then plus a second matrix, which has zeros over here. So as a result of those 2 values here are 0. And we have the update in the y and the z directions, which are mapped here as the updates in y and z. So that the new screw-symmetric matrix is a sum of the screw-symmetric matrix of my initial guess plus the screw-symmetric matrix of my corrections that resulted from the corrections that I've done to my baseline vector. Okay, so with this, adding this screw-symmetric matrix, or the sum of 2 screw-symmetric matrices, which gives me again a screw-symmetric matrix, would be the change that I need to put into my coplanarity constraint to see how the equation changes if I perform an update with respect to my baseline vector. And I can now do the same thing later on also for the rotation matrix. So again, these are my 2 unknowns. Now let's do the same thing for my rotation. So how does a change in the rotation matrix actually look like? And here we have to linearize and use the linearized equation for the rotation. Remember, the rotation matrix contains the sine and the cosine, so these are nonlinear functions in here. And here now it's beneficiary that we started with the identity matrix so that we are in the stereo normal case and then only have small updates with respect to the stereo normal case. So my new rotation matrix is the rotation matrix that resulted from my initial guess plus a small tiny differential rotation, so small rotation in your pitch roll that I can add to this initial guess. So the rotation matrix of my initial guess is the identity matrix because both cameras look into the same direction. So the second camera is not being rotated with respect to the first camera. That's my initial guess. And then I update this small change and I can express this through a screw-symmetric matrix where the vector encoding the change in the 3 rotation parameters is put in as the parameter of the screw-symmetric matrix. So it's kind of the differential rotation in 3D. So this rotation matrix basically consists of an identity matrix plus this screw-symmetric matrix over here. So this is my correction in the 3 unknown parameters that I can apply. And again, here the simplification again comes into the game that we are in the stereo normal case, or we're starting from the stereo normal case, because otherwise this wouldn't be the identity matrix over here. We would have the sine and the cosine of the individual solution in here, but if this is identity matrix, this is a result because the sine and cosine operation of 0 degrees gives me 0 and 1. So as a result of this leads me to an identity matrix. Okay, now what I have done, I've looked how do the individual changes in the parameters actually look like if I apply small corrections in the baseline and small corrections in the rotation parameters. And this would lead me to the coplanarity constraint that if we are close to the stereo normal case, that means it must hold that I have my x prime and x double prime over here and my screw-symmetric matrix describing the baseline vector. And again, we are close to the stereo normal case, but now we have the small changes in Bz and By taken into account. So we still assume we start from the stereo normal case, but then can apply small changes with respect to the baseline vector and also with respect to the rotation matrix. So we're starting with the same orientation of the camera, and then it can apply small changes to one of the cameras. So a small roll, a small pitch, and a small yaw angle. And this is encoded in those parameters, these three parameters over here. Okay, so this is the coplanarity constraint if we are close to the stereo normal case under the assumption of this linearization over here. Okay, so we start with this coplanarity constraint and now can write down the linearized error function through the initial guess that we have exploited and the total differential, so the sum of all the, which is basically the sum of all the partial derivatives. So we start here with our configuration from the initial guess, this is where we started, and then we look, okay, what happens if we change, or we have a small change in the pixel location of the first point that I'm observing? Then all the parameters stay the same except of this small change in the pixel coordinate of the first point. So this x prime gets into my delta x prime and the rest stays the same. Then I have an additional term. What happens if I incorporate a change with respect to the second pixel coordinate? So this is what I have over here. So this x double prime from here gets replaced with this delta x double prime. And let me do the same for the baseline vector or the skew symmetric matrix of my baseline vector and the rotation matrix. So I have here the small update to the skew symmetric matrix and the differential rotation which sits in here. And based on the coplanarity constraint, this should be equal to 0. Okay, so what we're now doing, we are starting with this equation over here, and we'll now do some operations on this equation so that we then, in the end, will end up with the equation of my Gauss Markov model. So we start with this equation over here, now do some manipulation to this equation so that we in the end up with a form, with an equation where we can see that this is actually the equation that I can use in as my Gauss Markov model equation. Okay? So we start with this and now do manipulations of those steps. And the first thing we do is we just expand all those quantities that we have described before, right? So this is my skew symmetric matrix, my rotation matrix, and we could put all them in place and basically take this expression, expand it by just filling in the definitions of the individual values. So we start over here. This is a copy-paste from the expressions that we've seen in the previous slide, and now we are just expanding it. So for example, let's look for the first line. This is the initial guess where I've, not the initial guess, the initial configuration where I have seen the point number 1. So this is x prime, y prime, and my camera constant c. And the same holds for the second vector. This is x double prime, y double prime, c. The rotation matrix of the initial guess is the identity matrix, and the skew symmetric matrix of the initial guess has no change in the y and z direction, so of only minus bx and bx over here. And now I can go through every line and expand all the expressions over here and see how the change in the individual parameters will lead to an update of this equation, right? So basically, how does this the whole expression basically describes me the coplanarity constraint if I'm deviating from the stereo normal case under variations of the individual parameters. So the first setup here is basically the initial guess, the standard, the stereo normal case, perfect stereo normal case. And then the second line over here is what changes if I have a change in my pixel coordinate in the first image. So there's a change in x prime. This line over here is exactly the same than this one over here, except that we don't apply the change in x prime, but in x double prime. So this is a change in x double prime. Over here, we look into questions, how does a setup changes if I apply changes to my baseline vector? So this is a change in the baseline vector, which will lead to a change in this skew symmetric matrix. And down here, the skew symmetric matrix stays the same, and we have our change in our rotation parameters. So what is the update of the rotation parameters starting from the stereo normal case, and how small changes in the yaw pitch roll angle will actually change so how does a change affect starting from that initial guess? So basically, the linearized equation over here which tells us how do changes in the individual variables will change the overall expression. Okay, now we have to sit down and perform all those matrix vector multiplications by hand in order to expand those terms over here. In the interest of time, I will do this only for the stereonormal case and kind of leave the others out. You can do this as an exercise yourself, but it becomes very clear that this is kind of just a little bit of manual work, but nothing which is necessarily very complicated. So let's look only into this part over here. How does this change? So the first thing we need to do, we need to multiply this matrix with this vector over here. So we have 3, 0, 0, 0 multiplied with x double prime, y double prime, c. So this vector, this column vector multiplied with this row vector over here will give me 0. So the first element of this resulting vector that is a result of the matrix vector multiplication will be 0. The second dimension would be 0 times x prime, 0 times y double prime, minus bx times c. So this is the only term which remains. So the second dimension will be minus bx times c. And then for the third dimension will be 0 times x double prime, bx times y double prime. So this will remain. And 0 times c, this will also be 0. So the resulting vector of this vector matrix multiplication will be 0 minus bxc and bxy double prime. Okay? So if I execute, that get 0 minus bx times c, bx times y double prime. And then our next step is I need to multiply this vector with this vector over here. And so that is easy. This is x prime times 0 will cancel out. I have y prime times minus bxc, this remains, plus c times bxy double prime. So if I perform this computation, then this is exactly the result that I get from this. And the only thing, or the quantity which appears multiple times in here is c times bx. So I can move c times bx out of the bracket so that then, or use a bracket, then what remains is y double prime minus y prime plus a factor. So this is my resulting solution, how this first expression looks like. So this first expression, starting from the stereonormal case, is actually lead me to this equation over here. And I'm basically repeating this process now for this line, this expression, this expression, this expression. Just perform this matrix vector or vector-vector multiplication and simplify those terms over here. So that in the end, all those equations that I get from those individual lines actually are not too tricky. They all look rather similar. The others are slightly more complicated, but not much more. So if you now sit down with a piece of paper and actually do the derivation by hand, you will end up with this expression over here. Again, this is the expression that we just computed on the previous slide. And then we have similar updates for all the other expressions. It gets slightly more complicated for the case down here where I have two matrices with a few more non-zero elements. So a few more terms actually remain over here. But this is now my final equation that I have. So let's have a look a little bit into the individual parameters that are actually involved in here. So let's look to this expression over here, y double prime minus y prime. So what is y double prime minus y prime? So this is the difference in the y coordinates of the corresponding point. So remember we have two corresponding, so one point in the 3D world which generates one point in image number 1. This is the y coordinate of this, and one point in image number 2, and this is the y coordinate of this. And in the stereonormal case, the difference in the y coordinates should actually be 0 because the epipolar lines are horizontal lines. So the y coordinate is basically the row index, and this should be 0 in the perfect stereonormal case. Right? So this is what we call the y parallax. So the y parallax in the stereonormal case should be 0. So what I have down here, I have here in the next line exactly the same, except that I look into the change in the pixel coordinate, in the y coordinate of the image point, image number 1 and image number 2. So this is basically the y parallax correction. So this tells me by how much the y parallax changes if I change the location of pixel location of point number 1 in image 1 or the same point in image number 2. So this is basically the parallax correction. What I down here have is the x parallax. So this is a difference in the x-coordinates of a point. And this is basically just subtracting the x-coordinates of the points taken in image number 1 and in image number 2. And if you remember the equations for the stereo normal case, this was giving you information about how far that point is actually away. So this is what's the parallax in the x direction, and this basically tells you from that further triangulation how far that point will be away. And then we have another setup here. What we have is x prime y double prime minus x double prime y prime. And now there's an approximation what we are doing. We're saying if we are in the stereo normal case, or close to the stereo normal case, I'm looking here into the change of the baseline vector in the y and the z direction, so this is where this expression came from, then I can say, I can assume that y prime and y double prime are approximately the same. Again, this is an approximation that we're doing here, but in this, if we want to make an approximation, we can replace this value by y prime, so y double prime by y prime, and then, because then this is the same equation, I can put it out of the bracket, and this can simplify our equations a little bit. So what I'm exploiting, I'm making this approximation over here. Again, this is an approximation saying y prime is approximatively equal to y double prime, applying this only to this expression over here in order to simplify my equation. And again, this is something, a simplification which only holds for the stereo normal case. So if I do this, then I can rewrite my equation like this. So again, this was what I had in the previous slide. So what I'm taking this bracket over here and this saying, okay, this is my y parallax. This is my change in the y parallax. This is my x parallax. This is also my x parallax, and so on and so forth. So I kind of slightly simplified this expression over here so that this is now the resulting equation that I have just from multiplying these vectors and matrices with each other, and then introducing those new terms over here as my y parallax and x parallax based on the definition of what the y parallax and the x parallax is. And the only approximation that I have done was in this row replacing y double prime with y prime, assuming that we are close to the stereo normal case. This is everything I have done so far. And now this is the resulting expression so far. And now let's inspect two quantities a little bit further, quantities I actually have started with. The first thing is this py over here. So this is my y parallax. And this term is important for me now because I can treat this as my observation in my Gauss Markov model, because that's basically what I'm observing, how large is the y parallax, so the difference in the y locations, in the y location of a point seen in image number 1, image number 2, and because this basically tells me how far I'm actually deviating here from the stereo normal case. So we target this py because this is a term which needs to be 0 based on the coplanarity constraint for the stereo normal case. So I can treat this as my observations. So if I treat this as my observations, the second term down here is actually the corrections to my observations, what I'm observing. And then I have other parameters, and those other parameters, or factors which are here, involve the change in the baseline vector in the y direction, in the z direction, and then also the different rotation parameters, being one over here, and the other one over here, multiplied with some other values. So these are actually my 5 unknown parameters and some coefficients. Okay, so what we can now do is we can take this expression, because in the end I want to have the observations being separated in the corrections of the observations. So I take this whole expression and divide it by c times bx. So I'm dividing everything by c times bx. So py remains here, delta py remains here. Here the c goes away, and they divide this expression by bx and do the same thing for all the individual terms of that sum. And if I do this and then move px and py and delta pi to the other side of the equation, then my resulting equation will in the end look like this. So I have py, delta py, and then some coefficient times the change in the baseline vector in y. So this should actually be a capitalized y, not a small y, so this should be capitalized. And here the same thing, my parameters and my change in my parameter in the z direction, a coefficient times the change in the first rotation angle, a coefficient times the change in the second rotation angle, and a coefficient times the change in the third rotation angle. Okay, and the equation that I now have ended up with is in the end the equation in my Gauss-Markov model. Why? This is my observation. I have the observation plus the corrections applied to, and then that equals two coefficients multiplied with the corrections in my unknown parameters, which is this one, this one, this one, this one, and this one. So I've come up with an equation that, based on just starting from the total differential and then doing some manipulations, so that I end up with my linearized equation for my Gauss-Markov model. Okay? So I can now rewrite this as we typically do. So take the coefficients and put them in a vector, take the unknowns and put them into a vector just to come up with my typical form. So this is copy-paste from the previous slide. I can just write this in vector form. So I have my coefficient vector, which only contains coefficients. And then I have my corrections in my unknown parameters, my 5-dimensional vector, which basically tells me the change in y, change in z, change in the yaw pitch roll angle that we have in here. I can express this for every single constraint, so for every corresponding point pair as this coefficient vector and the update in the parameters. And on the other side, I have my observations and the change in my observations. Okay? So, and this is now exactly the same thing that we have our standard Gauss-Markov model equations with observations, corrections, coefficients, and parameter updates. And if I have multiples of those observations of multiple corresponding points, every corresponding point gives me one row in this equation. So the observation of the first corresponding point, the second corresponding point, the third corresponding point, until the nth corresponding points, the corresponding corrections, and then the coefficients for every point pair that I'm seeing, and then the resulting update of my parameters. And this is now kind of the standard equation that we know, and from this point in time on, we can basically go ahead and apply our least squares toolbox and come up with a solution. The only thing we need to specify is the uncertainties, but that's fairly straightforward because we said before that we measure our point coordinates all have the same uncertainty. So we have our diagonal matrix of the pixel observations. So I have a standard deviation in x and y. We have to be slightly careful in here is because we are now looking here into the x-parallax. And the x-parallax is computed from an observation of the y-coordinate in image number 1 and in image number 2. So the variance of this is actually the sum of the variances of the individual uncertainties. And if we now assume that I can measure both coordinates in the same way, that means the standard deviation of my observation here is the square root of how precisely I can actually measure in an individual image. So it's the square root of 2 times the uncertainty how precisely I can pinpoint down a single point. This is the uncertainty of my observations because I treat the y-parallax as the observation here and not the individual pixel coordinates themselves. But of course they are directly related because from 2 pixel observations I can obtain my parallax observation. So that the uncertainty of my observations is a diagonal matrix which exactly has this term squared on its main diagonal. Okay, so it's fairly straightforward. It's just a factor which is additionally added to that to the uncertainty of my observations. So, and this is an n by n diagonal matrix, taking into account the n is the number of observations that I have, the number of corresponding points that I have, and the corresponding elements on the main diagonal. And from this point on, I said, just take out our least squares toolbox and can solve this. So what we have done, we have computed the linearized error equation. We have the observation covariance matrices just from the previous slide. And then we can build our normal equations using our coefficient matrix A transposed, the inverse of the covariance matrix that we just specified times A delta X. So this is a matrix. This is my normal matrix, or the matrix for my normal equations, typically referred to as N. And then here, this is the vector on the right-hand side being constructed from the A transposed, the uncertainty of the observations inverted, so the information matrix of them, times my delta L. And I can solve this system as my update being in this form over here, although I often would not explicitly invert this matrix here. I typically compute this using, for example, Cholesky decomposition, which gives me an update in my parameters, and I can also obtain the updates for my corrections, either the whole correction vector or the corrections for the observations in the y-parallaxes for every individual point. And this is kind of the standard out-of-the-box least square toolbox that we have been using in order to compute the updates of the parameters. So what we have done so far, we have presented an iterative solution, or iterative least square solution, to the problem of computing the relative orientation for a calibrated camera pair. And we have done this under the assumption that we are doing this for the stereo normal case. So what we have derived in here happened only for the stereo normal case. If we go to the general case, where we have general camera configuration, it gets more complicated. Here we said our initial guess is a stereo normal case, and we just have small deviations from the stereo normal case that we are actually seeing here. And this is a simplification. But if you don't do the simplification, it gets much more complicated. And as we'll later on see, we can use the result that we have in here for the stereo normal case in order to quantify quite well what precision we can actually expect if we take observations with two cameras in a similar setup. We have derived all this starting from the coplanarity constraint, performed our linearization, started from the total differential, and then resulted in, after some manipulation, into a Gauss Markov model equation. So where we have our observations, our corrections of the observations equals to a coefficient vector times the update of my parameters. This then leads me to a linear system that I need to solve. And then solving this linear system then results in obtaining, computing those corrections that I have. So this was now the way how we can compute the iterative solution for this relative orientation. So the next thing we can actually look into is asking us the question, how good is actually the result of that solution? So what we have done so far, we have set up our least square system. We looked how the parameters, how does it change in one parameter affects my solution. But the question is, if we have done this now, how good is my result? Did I do a good job or a bad job? What can I say about the resulting uncertainties? And that's something that we can investigate now. Before we want to talk about the quality, there are different ways how I can actually measure this quality. And these are kind of three important quantities here, which is the precision, the trueness, and the accuracy. And before I continue with this, I want to very briefly talk about that in order to differentiate those quantities here and here. So the first thing is the precision. The precision is basically how close or how similar are the results of independent tests that are executed under the same conditions. So I'm having an experiment, I'm repeating this experiment, and how well do those experiments agree with each other? So if you have sample points, for example, which are always the output of your test result, it is basically the variance of those test results that we have. But just one result with respect to the other, not taking into account the true location or the true configuration. And then we have the trueness, which tells me how far am I actually away from the actual result. And here we are looking basically, if we repeat our experiment and we compute the mean of the results of those experiments, how close is this to the true value? So the closeness of agreement between the average value obtained from a large series of measurements, these are all my experiments, I'm computing the mean of this experiment, of all those experiments, and seeing how far is this away from the true value. This is what the trueness tells me. So if I'm repeating an experiment over and over and over again, compute the mean of that, how close is this to the mean? And then the accuracy is the closeness of the agreement between the test result and my true value. So what does it mean? We can actually quite nicely illustrate that with this plot over here, which stems from one of those ISO definitions of this. So if this is where my true result actually is, and those dots over here are the result of my experiment or my measurement, then if I have my points over here, let's say these are the results, so there's a spread, and the mean of those results will be lying somewhere over here. If I'm increasing trueness, actually moving up on that scale, that means the mean of those experiments moves closer to the center over here. So this you can see here. So those points, the mean of those points will be somewhere much closer to the center compared to the setup over here. So this increases trueness. That means the mean of all the measurements or the results get closer to the actual value. If I'm increasing precision, I'm basically reducing the variance of those points. So those points get closer to 1 point. So the spread between the mean of this experiment and the individual experiment gets smaller, as you can see over here. It doesn't mean that you're moving closer to the true value. It just means if you repeat this experiment, the results will be more similar to each other. And so you're reducing this. So the points are closer to each other. And of course, what we typically want, we want to have an increased accuracy, which is basically optimizing for both. So we want to reduce we want to increase the closeness of the mean of the individual measurements. They should be closer to one value. And this value should also be closer to my original solution. That's what we see over here. So here I have my results, and the mean of those points is pretty close to the true value. And this is what we refer to here. That's what we actually want to have, but the accuracy is typically hard to measure because in most of the time we don't have the true values available, only if we do controlled experiments in order to verify this. So what we can more easily measure is actually the precision, because this is something that I can actually determine without even knowing the true value. And so for those of you who are studying here in Germany, there's basically the English term and the German term. So Precision is Präzision oder innere Genauigkeit oder Wiederholgenauigkeit. Trueness is, we refer to in Germany as Richtigkeit. Accuracy is die äußere Genauigkeit. And we can also look into the reliability oder die Zuverlässigkeit. So you have to be a little bit careful if you translate those terms. If you just use the term Genauigkeit itself, it's a little bit unclear if you refer to the accuracy or to the precision, so you have to be a little bit careful with those terms. So I will stick here with the English terms: precision, trueness, accuracy, and reliability in this course. And what I want to investigate now is the precision. So the precision of the relative orientation is the quantity that I now want to investigate a little bit further. So the question here is, how large is the influence of random noise on my result? And we can, based on the least squares approach, know what precision my resulting system has. And we have two quantities in here, the theoretical precision and the empirical precision. And they are computed from the system, from the matrix of the normal equation system. So A transpose, the covariance or information matrix of my observations, A, and if I invert this term, so this is n inverse, this gives me the theoretical precision after I converge to my solution. And the theoretical precision and the empirical precision are identical up to a scale factor, and this is the variance factor. And the variance factor basically takes into account the remaining residuals that I have and the number of observations minus the number of parameters that I actually need to estimate. And what I typically want to have, if my model choice was right, I want to have a variance factor that is close to 1. So how do I compute it? So the variance factor can be computed as the sum of the residuals, here called omega, divided by the redundancy. And so this term over here is basically the sum over all of the residuals, so the corrections to my observations, and multiplied with the information matrix telling me how much information I have about them, or the inverse of my uncertainty that I have. And this basically means summing over all observations over all corresponding points in here and computing this term. And this we then divide by the redundancy R, and the redundancy R is the number of observations that I have, so n because I have n corresponding points, and minus the number of unknowns, which is in our case 5, because we have 5 unknown parameters. 2 for the baseline vector and 3 for the rotation matrix. So this means this variance factor is this term over here divided by n minus 5. And so I need to have a redundancy of a certain magnitude in order to get good solutions for the empirical precision. So if R equals 0, then we will actually have a unique solution, right? If R is smaller than 0, that means actually we can't resolve it. We don't have enough observations in order to determine my unknown parameters. And if R is larger than 0, then we have to do the least squares approach. And as a rule of thumb, we can say if R is larger than 30 approximatively, we get reasonable results for the uncertainties. So if we have whatever, let's say 35 corresponding points, we subtract from this my 5 unknowns. So I have 30 as my redundancy. From this point on, I can expect to have realistic estimates of the empirical precision for my parameters. So I need approximately 35 corresponding points in order to get reasonable results. So this is my variance factor as we described it before, and this is the inverse of my matrix n as described before. This gives me then the empirical precision of my parameters, so in terms of the baseline vector and the rotation parameters, so that I can then extract the standard deviation as of, for example, by as taking the first entry, the entry 1, 1 of this covariance matrix, and computing the square root. And I can do the same thing along the main diagonal of all the quantities that I want to estimate. And this then provides me with information how certain I am, how good is my solution. So I can actually compute it, but again, keep in mind, the values are good if your redundancy is around 30 or larger. So this is one way how I can evaluate the quality of my result in terms of the precision that I have. A second thing I may want to look into are the correlations, and can compute the correlations between the parameters. So I compute this between my 5 unknown parameters, and I can use it in order to check those values. So in terms of large correlation, that means values approaching plus 1 or minus 1, sorry. Then this can actually lead to unstable solutions. So if I would get exactly 1 or exactly minus 1, then I have issues solving my system because I end up having rank deficiency. But if these values are close to plus 1 or minus 1, then I can have an unstable solution. So I may want to verify that those values are not close to plus 1 or close to minus 1 to make a statement about the solution that I'm actually getting. So this was now kind of the general setup, looking to which statements can I make in this close to stereo normal case. But in the setup, if I would do this for the general case, of course, the equations would be transferable one-to-one in estimating my parameters. Only you would need to change your coefficient matrix A and replace it by the correct coefficient matrix. This is the thing that you would need to do then. What we now can do as a next step, we can say, okay, let's take a stereo normal case and a controlled set of points and estimate how precisely I can actually compute my relative orientation, or which parameters impact the quality of my result. And this is something that we do using the so-called Gruber points. And it's a standard procedure. It's also around since a very long time in order to estimate that quality. And these are basically in the standard setup 6 points, 6 so-called Gruber points. You can also use Gruber double points. Then you replace every point with 2 points, so you have more measurements available. And you have 2 images. So this is image number 1, and this is image number 2, and you have 6 points, point 1, point 2, point 3, point 4, point 5, point 6, ordered in this number. And you have an image overlap in this example of 60%. And so you get 2 images, one which looks like this, and the other one which looks like this. And so you have those correspondences, 1, 1, 2, 2, 3, 3, 4, 4, and so on and so forth. This is kind of the geometric setup when you overlap those images. And the question is, with those 6 points, how precisely can I actually estimate my 5 unknown parameters, so the change in the baseline vector and the change in the rotation parameters for the stereo normal case. And this is what we call the evaluation of the quality using my Gruber points. In this setup, we have 6 corresponding points. We have an image overlap, so how much do those images overlap by 60%. We assume here the same uncertainties of the points, so I can measure all points in the same way. And then the basis vector is basically given by the image scale number times my image basis in my image. Okay, so what I have those points. Those points are in the x direction have a displacement of b, and in the y direction a displacement of d. And what I now can do is, based on the setup, I know where I'm actually observing my points. Okay, so I have my b and my d, and now can express this in a coordinate frame, center the coordinate frame over here. Then in the first image, so this is this image over here, and this is the second image, the coordinates of my point 1, 1 would be 0, 0. The coordinate of this point in image number 2 would be 0 for the y coordinate and minus b in the x coordinate. So this was basically the overlap of the images where I see my point 1 in the other image. And then, so this point 2 is then in the y coordinate is 0, so it's centered always in the principal point. And so this point has an x coordinate of b. And in this way, I can specify the coordinates for the individual points with b and d, and so have now specified my image coordinates. And remember, the location where those points are in the image will help you, or will tell you how precisely you can actually pinpoint the individual points over here. So depending where those points are in an image will give you different results, and therefore it's important to, or you can only investigate that for one geometric configuration, and now we have this configuration where we have 6 points basically distributed over the overlapping area over here. So if we do this, if we have those parameters, what we then can do is we can compute my coefficient matrix A, because in this coefficient matrix A, we have the pixel coordinates in there. So I have my Gauss Markov model. So this was the coefficients that I had for my parameters, and this gives me a coefficient matrix where I now have my B's and my D's being cluttered all over my matrix A, based on this coefficient equation. So this is for the first point, for the second point, for the third point, fourth point, fifth point, and sixth point, the individual coefficients. So this is the coefficient for the first parameter, the coefficient for the second parameter, coefficient for the third parameter, coefficient for the fourth parameter, and coefficient for the fifth parameter. That's the way how I build up my matrix. So point number 1 till point number 6, and first coefficient up to fifth coefficient of my first unknown up to my fifth unknown. The next thing I need to do is I need to compute the matrix A transpose A, assuming that all the weights are equal, and then it's just kind of a constant factor. We assume a weight of 1 in here, so I have a standard deviation of 1 for all the points that I'm actually measuring. So if I'm now computing A times A transposed, something you may not want to do by hand anymore, that you will end up with this matrix over here. You can see some of the elements are 0 and other elements get filled with equations containing the B and the D, so the distance of the point in the x and y direction, the camera constant, and my Bx, my constant offset for the stereo normal case, so how far the cameras are away in the x direction. What I then need to do, I need to invert this matrix if I want to compute my precision. So for computing the precision, so this is now my n matrix, I need to actually invert this matrix. I can invert my matrix, and then this would be the result. This is the inverse of the matrix, and I multiply it with my variance factor. So that in the end, this is the equation that I'm interested in looking into, because this term over here gives me the precision in the first coordinate, so in the update of my baseline vector in the y direction. The update in the z direction, the uncertainty of my first rotation parameter, the uncertainty of my second rotation parameter, and the uncertainty of my third parameter. And then would need to take the square root out of this in order to get the standard deviation. So from this equation, I can directly get the uncertainty in the 5 unknown parameters that I have, given by those expressions over here, and these are just obtained based on the main diagonal elements of my matrix to come up with the precision. Okay, so these are my terms over here. Now let's have a look. What does this actually mean for me? So what is the impact of the individual parameters that I have? So the first thing I can see here, all those terms depend on how precisely I can estimate the locations of my points, and especially the location of the y parameters of my points. So how precisely I can measure the y coordinate of every pixel point has a direct linear dependency on how accurately I can determine my parameters. So the better I can measure my points in the image, the more precise my parameters will be. This is probably something which is not a surprise. The better you can measure or pinpoint your points in the image, the better your parameters will get, because these are your observations, the parallaxes that you're observing, and so there's a direct relationship between how precisely you can measure and the results of your parameter. That's a linear dependency, as you can see in here. So there's no square root, or something like this over here. There's a direct linear relationship, so the more accurately I can measure my parallaxes, the better my result will be. Not a surprise, but you can see this direct linear relationship here. Okay, so then the next thing we may want to look into are those values B and D over here. So there's D popping up here, there's B popping up here. So some of those values actually can be seen as squared values. Some of them there's only a linear dependency in there. But what we can see is the larger the scene and the overlap of the images, the better the result. So if I'm increasing B or increasing D, they are all sitting down here, those values. If I increase those values over here, the uncertainties of the parameters will drop. That means the larger the points are spread over my image, or the larger the scene is, the better the result will be. So the more precisely I can pinpoint my points. So if all points are sitting in close to the same location, the uncertainty of my parameters will be very big. If I'm spreading that all over the image, that is much better and will give me better parameters for my baseline in Z and the rotational components in here. Okay, so the larger the scene and the overlap, the better my result will be. And then I can also look into, again, especially the roll and pitch parameters I have here. So these were those two parameters over here, because here the quantity is actually a quadratic dependency and here it is only linear dependency. So for those two parameters, the spread of those points, how the points are spread in the scene. So this one over here, as well as this spread, strongly impacts the estimate of the pitch and roll. So as a reminder, this was kind of the roll angle of the camera and the pitch angle of the camera, which obviously depends how those points are spread, and it's actually a quadratic dependency. So the more you spread those points, the more precisely you will be able to pinpoint or to find the correct roll and pitch angle. And last but not least, we have the camera constant in here popping up in all terms except of the yaw angle. And so the smaller the camera constant, when generating identical images, the better the result will be. So the smaller the camera constant, but of course then you also need to change your scene setup. If you still observe the points at the same locations, then the better your result will finally be. And also a final word to the image scale number. So the smaller your image scale number, or the larger your image scale, which is one is the inverse of the other, the better your result will be. So the smaller the image scale number or the larger the image scale, the better is your result, but here not impacting the rotation parameters, only affecting the baseline vector. So with those equations, we can directly see how the spread of the points over the scene impact the results of the quality that I get for my relative orientation, and also how the camera parameters affect this result. We can also do this for the for Gruber points if I don't take 6 but 12 Gruber points, and the so-called Gruber double points, where I use the points at the same or nearby locations. So I basically have double points, so I get not only 6 observations, I get 12 observations. The rest of the setup basically doesn't change. It's the same setup except that I have a larger number of points. And as a result of this, if I have 12 points except of 6 points, I have I get a different result because the uncertainty in my parameters based on 12 points and 6 points differs by a factor of 0.5 because I have more measurements. I can more precisely pinpoint down my points. So the more points I have, the better those results actually get. So if I have twice the number of points, it goes down here to half of the uncertainty of the variance, half of the variance that I actually have. Furthermore, of course, it is important to note the larger the number of points, the easier you can detect outliers. And this is also a very important point in here is if you only have the minimum number of points that you need in order to perform your estimation, you're very sensitive with respect to outliers. And it's basically impossible or hard to detect outliers. If you have a larger number of points, then you can actually more easily detect your outliers. And so this is also something that you need to take into account if you look into how many points you should actually have in your scene. With this, I'm coming to the end of my lecture today. So what we looked into was the estimation of the relative orientation just from corresponding points. And we have done that not in a direct solution, as we have done it before. We have done it in an iterative solution. And we looked here into a special case, the stereonormal case. So we are starting from the stereonormal case and only considered small variations from this stereonormal case and came up with a solution for computing the relative orientation with the least squares approach. And we have done this only basically for one iteration. So we haven't relinearized the result because in the next step we would have left the stereonormal case and then it gets more tricky. But what we have presented is the statistically optimal solution. Again, if you want to do this for the general case, you need to take all changes into account. And we don't have the simplified setup of the stereonormal case, which simplified our life in here. But you can also do the same thing in the more general setup. And then we looked into the result that I get. So what is the uncertainty of the individual points? And then looked especially into the Gruber point setup. So for the general case, I cannot say, if I have a general distribution of points, I cannot say what is the quality of my yaw angle, for example. I can only say that for a given setup of points. And we looked into one specific setup of points, one geometric setup of those points, the Gruber point or the Gruber double points, for which I then can make a direct relationship and can say how which parameter impacts which, or how which configuration, how the points are set up, impacts the unknown parameters of the relative orientation that I want to estimate. And as is always the case, the more points you have, the better your result will be. Again, the direct solution is still a commonly used tool because the direct solution provides the initial guess for the iterative solution. So even if you are not in the stereonormal case and you want to go for the general case, there's still the need for the direct solution that we just discussed before, so the 8-point algorithm or the 5-point algorithm for the essential matrix. They are still needed. They are still a key ingredient in order to get an initial value, to start your least squares approach, and they are also very helpful if you use outlier rejection techniques such as RANSAC in order to identify which points are inliers, which one are outliers, so that you then can continue working with your inliers in the least squares setup. Okay, so that is from my side. I hope you understood and get some insight about the relative orientation and how the arrangement of points impacts your results, how precisely you can nail down your 5 unknown parameters of the relative orientation. So, thank you very much for your attention.